So now we know how to calculate determinants efficiently. If we're given a matrix, then we can a square matrix, then we can row reduce it to echelon form without doing any multiplying rows by non-zero scalars. We don't have to do those to put it into echelon form. And then the determinant will be the product of the diagonal entries of that reduced matrix in echelon form. So, what we don't know is that that is a well-defined process, and we don't know that determinants always exist. We don't know that the determinant function is a well-defined function. So here, so like I said, to calculate the determinant of a matrix, we reduce that matrix to echelon form, call that matrix B, and then the determinant of A is equal to plus or minus the determinant of B, and that plus or minus is just determined by how many row swaps we did along the way of row reducing. So the issue here is that we don't know that the determinant is actually a function. What I mean by that is that it's not clear that we're always going to get a unique output for this function depending on our input matrix A. And the reason being, so the only way that we know how to calculate it as of now is by doing this whole process. And we've seen before that the echelon form of a matrix is not unique. So there's no reason to believe that the product of the diagonal entries, plus or minus the product at that, would be a unique value. So as a quick illustrative example here, let's calculate the determinant of this matrix. So I will row reduce it as follows. So I'll do -3 times row 1, add it to row 2, and replace. That'll make this first entry a 0, and what will that do for the second one? Well, I'm adding -6 to 4, so that'll be -2. So the determinant is equal to 1 times -2, which is -2. Cool. However, I could instead do a row swap first. So swap row 1 with row 2. And then I get 3, 4, 1, 2. And then I could take -1/3 times row 1 and add that to row 2. So the first row will still be 3, 4, and now the second one will be 0. And I think this should end up being 2/3. Right, -4/3 plus 2, which is equal to 6/3, is equal to 6 minus 4, which is 2 over 3. Cool. So anyway, here the determinant is equal to 3 times 2/3. But also I did a row swap at the start, so that should make my determinant negative. And of course this is equal to -2. So I just happened to get the same thing in both cases, but it's completely unclear why I should be getting the same thing in both cases. Because one, my diagonal entries are completely different. And two, over here I'm doing a different number of row swaps than I'm doing up here. And this is just for 2x2 matrices. It's not clear at all why this process would give me a unique, well-defined answer for 2x2 matrices, let alone size 25 square matrices or something huge. There are so many choices that would go into row reducing a matrix like that, and it's completely unclear why these choices don't matter. So the fix to all of this, the idea, is to use what is called permutation expansions. And what these are going to do is they're going to give an explicit formula for the determinant of A that is just going to depend on the matrix A. It's not going to depend on any choices for like your row swaps or row reductions or anything like that. We'll maybe see later that there are some choices that you have to check don't matter, but those choices are a lot easier and more manageable to check that they don't matter than the choices that we had in like the previous process. So here's some motivation. So first note that the determinant function is not a linear function, right? Linear functions satisfy or they respect addition. So you would say, okay, is it true that the determinant of A plus B is equal to the determinant of A plus the determinant of B? And you could ask, is the determinant of constant times A equal to K times the determinant of A? So let's do an example here. So here is the matrix A equal to 1, 2, 2, 8. I am going to look at the second property of linear functions, which says that is the determinant of 2A equal to 2 times the determinant of A. So 2A is equal to 216. Nope, that's the wrong entry. That'll be 2, 4, and this one will be 416. 2, 4, 416. Yep, okay. So if I calculate the determinant of 2A, so I'm just going to go ahead and use the formula for determinants of 2 by 2 matrices. So this would be 2 times 16 minus 4 times 4. So this is 32 minus 16, which is 16. And if I were to instead do 2 times the determinant of our original A, that would be 2 times the determinant of A is 1 times 8 minus 2 times 2. So this is 8 minus 4, which is 4. 4 times 2 is 8. So these two things are not equal to each other. So the determinant is not a linear function because it doesn't satisfy that second property. And I'll leave it as a open question to you all to think about whether or not it satisfies, whether or not it respects addition. Okay, so what you can say, so it's not linear function, but maybe let me just say let's work with the matrix 2, 4, 4, 16, and let's calculate the determinant of that. So I'm going to put vertical bars here to symbolize the determinant. So the determinant of this, so remember we're allowed to multiply rows by scalars, and that changes the determinant. Effectively, what that means is that you can pull out from each row a factor of that row. So the first row, I can factor out a 2 there, and so I can factor out this 2 from this row, and that'll effectively change the determinant of that way. So what I'm saying here is that so this matrix here, row reduces to this matrix here by multiplying row 1 times 2, and therefore the determinant of this matrix is equal to 2 times the determinant of this matrix, which is why I can effectively pull out this 2 here. You could also pull out a 2 from the second row. So that'll make this a 4 now. So this will be 1, 2, and now this will be 2 times 8. And so you could do that too. So what's going on here? Sorry, let me back out. So I'm not sure why I can't scroll sometimes when I'm using this app. Anyway, so the property that I was kind of illustrating over here, right here rather, is called multilinearity. Linearity? Yeah, multilinearity. So a map is multilinear if the following holds. So first thing is we're going to do it for arbitrary vector spaces, not just R. What you want to think of V as, you want to think of V as being equal to R to the n. It's going to be the same n as this here. And so we're going to take a map F from V to the n, which is basically going to be, so that's R to the n to the n, which is effectively going to represent n by n matrices. More on that later. So a map is multilinear if f of, so let me just say what this is, row 1, row 2, and then like for row I, I'm going to split up row I as some vector v plus some vector w, row n. And you can split this up as row 1 through v through row n plus f of, and then over here I'm just going to have a w. So effectively I'm just like splitting up one row here into its two components. So here's what I mean. Let me explain more what I mean by thinking of v as Rn and what I mean by this notation here. So v being Rn, each row I in Rn is going to be a row of an n by n matrix. So because we're in v to the n here, then that means that I'm going to have n, each element of v to the n is going to consist of n components, so row 1 through row n, and those n components are all going to be rows. So so v to the n really is just representing matrices here, and this is just some weird notation that represents some matrices. So this effectively is telling me that I can split up a matrix into f of one matrix plus f of another matrix, where the only difference between these two matrices is that one row was split into one vector plus a different vector, or one like row plus a different row. Okay, I'll give you an example of that right after I finish this definition. And then the second part of the definition says that if I have one row being multiplied by a constant, then I can factor that constant out of the entire matrix, well, f of that matrix. Okay, and this we've already done an example. This is exactly the property that I was doing over here. So this says that if one row is 2 times a different row, then I can factor out 2 from the determinant here. So what I'm trying to say here is the following lemma, which says that, oh, well, that'll be the next section. The lemma is going to say that determinants are multilinear. And, well, before we get to that section, I think it would be good to give an example of what I'm talking about here, and then I'll do more with that example in the next video. So let's illustrate property 1 here. So property 1 says, f F, this map, we're just going to think of F as being our determinant, because determinants are going to be multilinear maps, and in the next video I'll tell you why that's true. We'll give you a sense for why that's true. But it's telling me that the determinant of, for example, what was the matrix I was doing up there? 1, 2, 2, 8. I can split some row up into the row 2. I can split row 2 up into the row 2, 0 plus 0, 8, and therefore this determinant is equal to the determinant of 1, 2, 2, 0 plus the determinant of 1, 2, 0, 8. And that's, why does it do this? That is what this property here is trying to tell us. Okay, so more on that next.